Okay, I think we can start this webinar now. First of all, a warm welcome to everyone who joined. My name is Niels Verdijck, and I will be your host today. Apart from being your host, I'm also the customer support engineer at Diabatix, so meaning that if you have any questions or if you do a project with us, you'll for sure get in contact with me again. A little bit of background information about myself. So when I was a student, I did my master thesis on topology optimization. So it's not a real surprise that I started working at Diabatix because topology optimization is the core principle behind our generative design tool. Okay, let's move on to the content of this webinar. So today I will show you why our generative design tool is able to return the most efficient design to the problem that you may have. And I will do that by using a battery cold plate as an example. As you know, the battery in a battery electric vehicle is made up of different modules, which you can see here on the slide before you. All of these rectangular shapes are the tops of each of those modules. And each module contains a given number of battery cells. When the vehicle is in use, those modules require cooling to prevent the batteries from overheating, in turn expanding the lifetime of those components. As I said earlier, our generative design tool is able to return the most efficient designs, and I will prove that by comparing our design to two conventional designs, a dimple design and an S-shaped design, but I'll come back to that later in the webinar. And during this webinar, I will also show you how to set up the cooling problem on our platform to benefit from our generative design tool. Okay, I think I covered everything I needed to say, so let's switch to the platform. Okay, so once you're on the platform, you'll get an overview of all of your project folders. These really help you to keep all of your cases organized. Let's go to the project folder attached to this webinar. As you can see, I prepared 3 cases, so 2 simulations of our conventional designs and 1 design case, so where we benefited from the generative design tool. Let's go to the case setup using the dimple design. So the case setup is where you specify all of the relevant information where the optimizer that the optimizer needs to take into account. In the case setup user interface, you'll get an overview of all of your CAD entities that you included. You'll also get an overview of all of your interfaces that you define. As you can see, I didn't define any interface. And you'll also get an interactive interface where you can play around with the CAD geometry that you uploaded. Let's do the case setup itself now, starting with the fluid region. So as you can see, our fluid region is perforated. These are all of our dimples. So this is really to increase the interface between the cold plate, so our metal cold plate, and our fluid. This will help increase the heat transfer coefficient. The first thing we need to do is specify that this is a fluid region. So that's the first thing you need to specify. Next, you'll give it a name. I used a rather uninspiring name called fluid. Next, we need to specify what material or what type of material the coolant is made up. So we use a water glycol mixture with a 40-60 distribution. And we fix all of those properties at 20 degrees. So this will really speed up the simulation and optimization process. You can, of course, use temperature-dependent properties if you really want. Next, we'll ignore any buoyancy and any radiation. So that's why these boxes are unticked. And we use the default turbulence model, which is K omega SST. The last thing we can specify is any volumetric heat source, so being 0 in this case, so we don't have any heat generated within the fluid region. Next, we need to specify the inlet and outlet conditions. So you'll need to include 2 boundary patches. So that's what these symbols mean. Starting with our outlet, we define a pressure outlet. Again, give it a rather uninspiring name, and then fix the relative pressure at the outlet being 0. You can, of course, use whatever relative pressure you want. It's just easier to specify 0. At our inlet, we specify a fixed flow rate inlet, so that, as the name suggests, fixes the flow rate that comes in. Again, we give it a rather uninspiring name. The first property that's required for a fixed flow rate inlet is the temperature. So we fix it at 20 degrees. The incoming coolant is at 20 degrees. Be careful though, you need to specify this value in Kelvin. So you need to add 273.15 to our 20 degrees, which is why you see the 293.15. Next, you'll have to make a choice between three properties. So you can either specify the inlet velocity, you can specify the mass flow rate inlet, or you can specify the volumetric inflow. I've chosen to specify the volumetric inflow. If you really want, you can add a rotation to your inlet. I didn't do it, so that's why it's empty. And these properties are only valid or only relevant if you include radiation, which of course you know I didn't. Our next catch geometry is our cold plate. So this is the metal housing which contains our fluid and acts as the interface between our battery cells and our fluid. So it conducts the heat away from the battery cells towards our coolant. Because it is conduction, we need to specify a solid region. Next, again, we give it a name. It's our cold plate. And as material, we'll use aluminum. Why aluminum, you may ask? Aluminum is a very soft material, or a soft metal, sorry, relatively speaking, at least. So making it easy to work with, and it's also rather inexpensive. Again, we will not include radiation. And again, we don't have any volumetric heat source, so there is no heat generation within our cold plate. You may ask yourself, looking at the regions folder or the regions tab, we didn't include any CAD geometry of the module itself, because there's only one reason. I'm not a battery expert, so I really simplified it and I just created or simplified the entire module to be a surface patch, which you can see here. So this surface patch represents the entire battery module. The surface patch itself is a heated wall, so meaning that the heat generation is just on the surface. It's equally distributed on the surface. Again, we give it a name. It's the battery cell, and we specify the amount of heat that's being generated or that needs to be evacuated to the coolant. These properties, again, those are related to the radiation, but seeing as we didn't include it here, these are not really relevant. That's everything that's required from the case setup. I hope that's clear. If not, you can leave your questions in the comment section below. A quick view to our S-shaped design. So as you will imagine, it's very similar. So again, we have a fluid region, we have our cold plate with our three patches, so our battery cell and our inlet and outlet patches. Again, no interfaces. And it's pretty much the same setup, but now instead of perforations in the fluid region, we added barriers. So the fluid really is forced to take this long S-shape or S-shaped channel. And all of these properties are of course the same. So again, outlet, 800 watts heat input. So everything is the same except of this fluid region. Okay, so this concludes the case setup for the simulations. Because I prepared this webinar beforehand, we don't have to wait for these simulations to complete. So we can immediately go ahead and have a look at the results. If you exit full screen, we can do something like this, where we have both conventional designs next to each other, making the comparison easier. So on the left, we have the dimple design, and on the right, we have our S-shaped design. If you look at the maximum temperature of the dimple design first, we see that the battery cells have a maximum temperature of just over 38 degrees, which is rather high. If you look at the S-shaped design, we see that the batteries have a maximum temperature of just below 31 degrees. So it's a massive, massive improvement compared to the dimple design. So based on this performance value, you would immediately say to me, but Niels, the S-shaped design is much better to the dimple design, so why bother? Well, let's have a look at the pressure drop. Because of the very long channel that the fluid has to follow, the pressure drop is of course very high, which you can see here. It is nearly 150 kilopascals. If you compare that to the dimple design, we see that the pressure drop is only 3.6 kilopascals. So it's another big difference, but now in favoring the dimple design. So we have to find the trade-off somewhere. We want to minimize the temperature, similar to the S-shaped design, but you don't want to pay as big of a price for the pressure drop, because the higher the pressure drop, the more beefy your pump needs to be, and the more expensive it will be, the more pumping energy it will require. So we want a pressure drop more similar to, or in the same order of magnitude as a dimple design, let's say 5.5 kilopascal. So that's some of the information we need to take into account when setting up our design case. So let's quickly do that. Let me go to full screen again, so it's a bit nicer for you. As you can see, I already finished the design case, but when we do the case setup, I will do a duplication, so I can really go through the entire case setup again with you, but now for the design. So let's do something like a generative design webinar. So the duplicate button, which you saw me use a few seconds ago, it's a real nice trick to save some time. For instance, if you want to optimize for another operating point, or if you want to do a sensitivity analysis, for instance, it's a real nice trick to save some time. What that button actually does is it copies the entire CAD geometry and the entire case setup to your new case. So you don't have to redo the CAD upload or specify all of the properties of the case setup. You can just quickly change whatever property you want to save some time. Okay, let's go over the case setup once more, because it differs slightly from the case setup of a simulation. Starting with our cold plate. So again, it's a solid region where we use our aluminum from earlier, and where we ignore radiation effects, and we don't want any heat going to. We don't want any heat to be produced in our region itself. Next, our battery cells, or at least our simplification of battery cell. It's again a heated wall where our 800 watts is equally distributed over the entire surface patch. The keen eye under you may have spotted this new symbol that appeared. This symbol represents whether or not there is a target active on that entity. And because we wanted to minimize the temperature, we have selected a temperature minimization objective with a weight equal to 1, meaning that objective has the highest priority, as 1 is the highest weighting value that can be assigned. Okay, let's then go to our fluid region. So as you can see, there are no structures in that region, so we really force our optimizer to start from scratch. We don't want to guide it to a conventional design, for instance. If you were to add barriers here, you would really guide it. It will really optimize the S-shaped design, but we don't really want that. We want to let the optimizer start from scratch. So our fluid region is again of type fluid, where we again use our water glycol mixture from earlier. We ignore any buoyancy and radiation effects. We can specify our K omega SST as the default turbulence model, and we don't want any heat to be produced in that fluid region. Next, the main or the biggest difference compared to the simulation cases from earlier, we have to include a design region. So this design region is a subregion of the fluid region, and the size of this subregion really tells the optimizer where it can and cannot place material. So how does a design region look like? So it's a design subregion type. I'm sorry, a big truck passed here by. I hope you didn't hear it. We can again give it a name, very uninspiring design. Then we have to select out of what material or what material can be added to this fluid region. We again, or I at least again chose to specify it to be aluminum because our cold plate is made of that stuff, out of that stuff. Next thing to select is the manufacturing type. So I chose to use CNC milling, but you can of course select something else like 3D printing, die casting, or sheet metal. But let's go with CNC milling. Next, the manufacturing settings that are applied. So I chose to select CNC milling 1 mm x-axis. So what does that mean? It's CNC milling with a resolution of 1 millimeter, meaning that the material that needs to be that's taken away is at least 1 mm thick. And the x-axis represents in which orientation the CNC milling tool works. So, for instance, if you look at the cut geometry here, especially at our red arrow, it points perpendicularly to our design region. So we want our CNC milling tool to take material away perpendicularly to our design region, so perpendicular to the screen. Okay, that's the design region. Our outlet patch is again a pressure outlet with a zero relative pressure condition. Our fixed flow rate inlet has again 20 degrees inlet temperature, the same volumetric inflow, but now, as you saw here, it has a target. It has a pressure loss constraint. This is real necessary to include that into a fixed flow rate inlet, because if this were to be excluded, so purely a temperature minimization objective, the trivial solution will be returned. You may ask yourself, what is a trivial solution? The trivial solution is a solution where the entire design region is filled with aluminum, and where the pressure at the inlet has increased to infinity, meaning that because of this very high pressure, this very high pressure, sorry, will really force the fluid through this solid design region. So this solid design region will become porous, which of course is unrealistic. There is no real pump. There's no pump that can reach this infinitely high pressure. So it's the best solution, but it's physically impossible in reality. So it's very important to include a pressure loss constraint. And because of our simulations from earlier, we can assign it a reasonable target, being 5.5 kilopascal. Okay, that's the entire setup. We can submit it. When submitting it, you'll have to make two choices. Either submit it as a detailed or as a conceptual. The detailed design is very accurate, as it says here, and gives very detailed results, and the results will also be manufacturable. However, it will take longer to complete. A conceptual, on the other hand, it's a good first estimation, as the results will be delivered fast, but the resulting design will not be manufacturable. So that's a trade-off to be made. It will be done faster, but it's not manufacturable. The second decision to make is how many credits to assign to this case, so either 85 or 100. The higher the amount of credits you assign, the more computational resources that will be made available for this case. So the faster the case will be completed. For instance, the difference between conceptual 100 and conceptual 85 is just 2 days, although these are just indicative numbers. It can be that due to a high amount of solid regions, or for instance, buoyancy enabled in your fluid region, these indicative values may change somewhat. Okay, so let's say a detailed 100. We have enough credits, so we can do that, and that's it. Now the simulation, nor the optimizer, takes over and will calculate the optimal solution. Of course, since I prepared it, I don't need to wait for the optimizer to complete, so I'll just click Stop Calculating. because we don't really need it to run. Be careful though, if you stop the calculating button, it will delete all the progress it made so far on the HPC cluster. So if you stop it midway in a design, all the progress is lost. So you can't stop and resubmit it again and hope that it will pick up from where you left off. No, you really have to be careful with that stop calculating button. Okay, so this concludes the case setup part of the entire process. So once the case setup or the case is submitted, the optimizer takes over, and that's the real beauty, in my opinion, at least. So the topology optimization, or the main principle behind topology optimization, is that the algorithm or the optimizer decides where and where not to place material, meaning that there's no real prior knowledge required to really come up with the most optimal solution. It's all mathematically determined. So anyone can really design, or at least on our platform, anyone can come up with a case setup, and the optimizer will return the most optimal design or the most efficient design. Okay, so once the optimizer has finished, the results will be pushed back to the platform, and the status will change from running to this green finished. So from the blue running to the green finished. And once that's done, you can you can just click on the finished case. It'll be redirected to the case summary tab, which you are already familiar with. Our platform also allows to visualize the results in 3D, which I already prepared. And so I already loaded on beforehand to speed up this process a bit. So what you can see here in green are the design islands, or the material that's added in the design region. And the blue and orange, those are just streamlines of the fluid. And the more red or the more orange, the faster the fluid flow, or at least locally. And the more blue, the slower the fluid flows locally. But when looking at the results, it's a very complex geometry. I for sure couldn't come up with it. Yes. And the nice thing to see is that the optimizer really takes care to help guide the flow as much as possible. For instance, here at the inlet, only a small portion needs to be bled off, and most of it is guided to the middle or to the lower section here. For instance, here you have a very high local velocity region, which makes sense, of course, because here the inlet at the left is a region with a low temperature, because all of the coolant here is still at 20 degrees, or enters at 20 degrees. So due to the conduction, a lot of heat from the battery can already be transferred to the fluid, which doesn't require as much fluid in that actual region underneath the battery cells. So most of the fluid will be pushed to the middle region, and especially here to the lower right corner, where it's much harder for the fluid to cool down. And when looking at the actual shapes of the islands, it's real nice that it really helps guide the flow in an orderly and nice fashion. So it's not a blunt, our optimizer is not a blunt tool, so it doesn't really just place material like cylindrical shapes, which will cause the pressure to rise locally. It really helps guide the flow. For instance, here, this elongated island here, it helps attach the flow, these islands on the bottom as well, but it really helps attach the flow to it, which causes the minimal amount of separation. So not a lot of pressure drop in that in the entire region. So that's why our optimizer can come up with these efficient designs. It really takes into account the entire flow optimization. Some other things that can be visualized on the platform at least is, for instance, the temperature, or you can visualize the temperature. Yes, you can visualize the temperature of, for instance, the battery cold plate itself and the battery cell or battery surface patch. Here we can really visualize it in 3D. So as perhaps I shouldn't. Yes. So as you can really see here at the inlet, the temperature is very low as expected because the incoming flow, the incoming coolant isn't heated up as much, and the further away or the more to the bottom right corner you go, the higher this temperature gets with the hot spot here, which not coincidentally coincides with a high velocity region in that area. So you can really see how the optimizer distributes the coolant to help cool down the entire battery surface patch, which is, in my opinion, very nice to see. Another interesting thing to look at, hide others, is the pressure drop throughout the entire fluid region, with the islands taken out of it, of course. And you can really see that the gradient evolves quite smoothly throughout the entire flow region. So it's very red at the inlet and gradually becomes more orange, more blue, very blue at the outlet, due to the fact that the islands really help guide the flow, so no real local high pressure drops. Okay, so this is what you actually can visualize on the platform. If this is not enough, you can always download all of the results and look, for instance, at it in ParaView. You can always download this step file of the design region. So all of our all of a step file of this can always be downloaded by clicking this button. Okay, then the last thing to do is compare the three results. So we have our generative design here on the left. We have our conventional design or dimple design here on the top. And our second conventional design or S-shaped design in the lower right corner. First, let's compare with the dimple design. So let's look at the temperatures, and we can see that our generative design really improved temperature-wise, or maximum temperature-wise at least, compared to our dimple design. So it decreased nearly 4 degrees. However, when comparing it to our S-shaped design, it is still a bit higher. So it's more than three and a bit degrees higher compared to the S-shaped design. However, this is no surprise when looking at the pressure drop throughout the entire fluid region. Oh. Yes. So you remember that for the S-shaped design, we had a very high pressure penalty for a very drastic improvement in the temperature, or in the maximum temperature. We see that comparing the dimples or the dimples design to the generative design, we see a marginal improvement or marginal deterioration of the pressure drop. But do remember that we have a very high or very much an improvement temperature-wise. So that's why the generative design tool can come up with such efficient designs. Okay, I think that's all I needed to include. Oh no, that's not the last thing I need to include, sorry. I need to do something else. I think I can understand that some of this I went through fairly quickly. You can always go to our documentation page, for instance, by clicking the question mark button, and you'll be redirected to our website, directly to the documentation page, where you can have a look through all of the help or all of the information that we provide about the platform. For instance, if you want to know more about the different targets, you can go to the design chapter to the targets page. For instance, go to all of the objectives, and you can quickly find a summary of all of the objectives that are included on the platform. And of course, this page is being kept up to date. For instance, if you want to have more information on temperature minimization objective, you can quickly go through it by just clicking the link, and have some information. So the name, what the goal is, mathematical formulation, where you can apply it to. So you can really find your way fairly quickly. Okay, so next is up to you. You can play around on the platform. You can always press the request access button, fill in all of your information, and then we'll get in contact with you, and you can play around with our software. Okay, I think that's all I need to include. Final thing to include is that we will be hosting at the battery showcase in Stuttgart later this month. So on the 30th of November until the 2nd of December, we'll be hosting or we'll be opening up a booth at the battery showcase, so you can really come and have a chat with us if you want to know more about battery cold plates. And you can find us at booth 6.236. Okay, see you there. All right, I think let me make myself a bit larger. Yes, we can go over to the Q&A portion of this webinar. First question is from Hannah. What are the security features of the platform? That's a very good question, actually. Wait, let me share my screen again. So our security features on the platform, if you are the admin user of your account, of your company, you can go to company profile. Oh, no, sorry, not company profile. You can go to data overview, and you have an overview of all of your projects and where they are located. For instance, this project, which can be found in the cooling jacket project folder, is stored on an IBM cloud service in Europe. You can also, for instance, if you hover over it, you can see 3-level encryption. So we really take your sensitive information very serious. Something else you can do when you click on the company logo is go to activity log. It will show you, if it loads, the log of all the logons when the last logon was and what its IP address was, which is a very nice security feature. And you can always go for the option of hyper protect, so where you upgrade your security to military grade storage protection. So if you really don't want to share your sensitive information, it's an upgrade worth including, although the default storage is already very much safe. Also, if you add custom material, it will only be visible in your library, so it won't be shared with any of the other accounts. So you can be sure that your information is secure. Next question is of Alain. What is the advantage of having CNC milling over sheet metal forming? That's a very good question, Alain. So yeah, I think most of you have some experience with battery cold plates, and will know that the standard manufacturing setting or manufacturing type is sheet metal forming because it's very cheap. CNC milling has the advantage that the islands are filled, meaning that it's easier for the heat to be conducted to the entire over the entire surroundings of the island. So it is not restricted by a thin sheet. Although CNC milling itself, it's more expensive, of course, because you have to post-process the chips that are milled off, and of course the tool itself you have to replace that often. So for high throughput, I would suggest to go to use sheet metal forming rather than CNC milling, which we have. No, it's not here. No, it's thermal interface, which we have a manufacturing setting, of course, for. Okay, let me quickly have a look at the time. I think we're all out of time, I'm sorry to say. I will close the webinar here, but do remember that I will answer all your questions via email. I thank you all very much for your attention. Wait, yes. I thank you all very much for your attention. I hope you learned something, and I hope to see you soon. Okay, take care. Bye.